introduce, he will come.
Yeah, sure. I think we still have a few more minutes, right? 3 more minutes.
Okay, okay.
We can wait for 3 more minutes and then we can start.
Okay.
In case anyone wants to come and join at that time. Is it today going to be all online?
Yes. Madam, 1 minute. I am waiting for another person. Okay.
Sure.
Madam, can we start?
Yes, please.
Okay, Raju, you please start. DK Raju? Dr. Raju? Raju, is it audible?
Sir, is it I'm audible?
Yes.
Hello?
Okay, you please start. Okay.
Yes, sir. Yeah. So, good morning, all of you. So, Madam Rukmi Datta, Madam, Professor Rukmi Datta, Madam, welcome and good morning, you.
Thank you.
Yes, Madam. Sorry for the delay.
No problem.
Sorry, Madam.
No problem. Go ahead.
Okay, madam. Okay, madam. Just so all the participants, thank you very much for attending this workshop. And first of all, I would like to congratulate Professor Silchar sir for arranging this type of very worthful GIAN course. And it is our fortunate that we are interacting with the foreign faculty like Professor Rukmi Datta. So before going to start the session, just I would like to introduce Professor Rukmi Datta. So Professor Rukmi Datta, currently she is working as associate professor in the Energy System Research Group, School of Electrical Engineering and Telecommunication at the University of New South Wales. Yes. And she received her PhD degree from University of New South Wales in the year of 2007 and Bachelor of Engineering degree from Electrical Engineering from Assam Engineering College, Guwahati, India in 1996. So before the current position, she occupied CMG. She worked with CMG Private Limited. Currently, it is Regal Deloitte, Australia.
Raju, your mic is off. You switch on your mic. Audio is not coming, Raju.
Now it is okay, sir. Now it is okay.
Okay.
So somebody switched off my mic, sir. Okay. So Professor Rukmi Datta presently working as an associate professor in the Energy System Research Group, School of Electrical Engineering and Telecommunication at the University of New South Wales, Sydney, Australia. She has received her PhD degree from the same university, University of New South Wales, in the year of 2007, and Bachelor degree Engineering from Assam Engineering College, Guwahati University, in 1996. So Professor Datta is a senior IEEE member since 2015 and an active member of several IEEE technical committees. She is the current vice chair of the IEEE IIS Electric Machine Committee. So she has published almost 30 SCI Scopus indexed journal papers and 91 conference Scopus indexed papers with aggregate of 1420 citations, 1420 citations, and H index of 21. She has gained 10 million Australian dollars for her research work from Australia Research Council's Discovery Projects, Australian government, and she is currently supervising 6 PhD students and 1 postdoctoral fellow. And earlier she has guided 15 PhD students and 3 MPhil completed. And she is the non-editor of IEEE Transaction on Industrial Application Society and IEEE Transaction on Energy Conversion. She is also a guest editor of Elsewhere's well-known journal, Renewable and Sustainable Energy Reviews. She had served as an editor of several other technical journals, including the special issue of MDPS Energies. So this is a brief, small introduction about Datta madam. Madam, you please carry on the session. Thank you, madam.
Thank you. I think I need access to share screen. It's coming.
Yes, madam.
I am not given the access to share screen. So you have to give me that access.
Yeah, host, please give the share screen option to madam. Silchar sir. Silchar sir.
Okay, I think it has come. Yeah, it should be fine. Okay.
Is it okay, madam? No?
Yeah, I think it is okay.
Ah.
It has come. Yeah, it has come. So thank you.
Yeah, madam. You carry on.
So thank you very much. Before we start today, actually, I would like to share the quiz outcome from yesterday. We have 39 responses. Thank you for those who responded, and hopefully today all of you are present, those who were there yesterday. We'll quickly discuss the quiz questions so that in case you have doubt, we can clear it. So first question was whether the magnetic flux behaves like a current in an electric circuit, and majority of you have said it is true, and that's correct. So does magnetic flux does behave like a current? Okay, so that this answer to this question was true. Then in the second one, the question was whether magnetic potential can be measured physically like electric potential voltage. So answer is false, and majority have selected false, so that's also correct. The third question was about Poisson's equations, whether it can be solved by using numerical methods such as finite element analysis. Again, majority of you have chosen true, and that's correct. Third question was whether the leakage flux is unavoidable when we have air gap in the magnetic circuits. Again, the answer was true, and majority have selected true. Then the next one was, what is the disadvantage of a permanent magnet device? So majority of you have selected the magnetic field cannot be varied. Yes, that is one of the key disadvantages. And second highest selection was high maintenance, since magnet can be demagnetized easily. This is actually not a correct fact. Today you will learn that magnet actually, especially high energy or high strength magnets, cannot be demagnetized easily. So, and permanent magnet machine doesn't need high maintenance. So this is, please, those who have selected, so it's a misconception. So be careful about it. Then the next one was about inductance. Is inductance always present when current induces current? Obviously true, and most of you got it as a true statement. Then the last one was about why saturation in a magnetic core is not desirable. Many of you have selected it to be because of non-linearity between B and H. Yes, that's true. That non-linearity causes many issues. So one of the reasons why you do not want to saturate your magnetic devices. And then some of you have selected that magnetic material will not be used fully. So this is actually not correct. Magnetic material, when it goes to saturation or about to saturate, you are already using it fully. And the third highest, because of iron loss, this is also actually incorrect. Whether we have saturation or not, magnetic device, there will be iron loss. Okay, so iron loss we cannot avoid. We can avoid saturation, but we cannot avoid iron loss. And even the magnetic device that are not saturated, they will still have iron loss. Okay. However, many of you have actually missed one very important disadvantage of saturation. That is that once your magnetic core is saturated, the inductance start to become a variable. Okay, inductance becomes function of current. So that could be very annoying, especially in electric motor control. In motor control, or even also for generator control. You have a model of the motor based on which you develop your controls. And in that model, you have constant parameters such as inductance. Now, if inductance becomes function of current, then your motor model is no longer accurate. And that causes in non-optimum performance on the motor, controller, etc. So that's another reason why you want to actually avoid saturation if possible, so that you can prevent this parameter uncertainty in the motor models. Okay, so I think there was this one, those who haven't selected it, hopefully today we have clarified it. And then the last question was what was the most difficult? So it looks like permanent magnet and renewable energy, both of them are coming as a two difficult concept. Hopefully today we'll be able to clear your lot of confusion or misconception about permanent magnet in our next part of the lectures. Okay. So that's the outcome of the quiz, as you can see, and you will get a grade at the end of the course, which will be summation of total 5 quizzes. Now let's go to our slides for today. So we will be today starting the first part of the permanent magnet machine. This first of 2 hours will be the lectures, that's basically theory. And then in the second half, we'll have a tutorial this time, not lectures. So in the tutorial, you will learn to apply some of the theory that we discussed in the lectures of the first 2 hours, okay? And tutorials will be conducted by Dr. Clay Chu, whom I will introduce in that's the beginning of the tutorial. And as I mentioned previously, we will have you can stop me anytime if you have questions, or you can hold up to your question till the end of our lectures. We'll have, like yesterday, at least 2 distinct parts in our lecture. So in the first half, we will have a quick review about synchronous machine, conventional synchronous machine, so that we can see the difference between a permanent magnet synchronous machine and a conventional synchronous machine. After that, we look at the property of permanent magnet materials, and then we will actually look at the working principles, type of permanent magnet machine, etc. All the basic fundamental theory related to it. Okay, so that's the idea. In the first half, that's why you have a couple of learning goals that after the end of the first section or first hour, we will be able to describe the main or key constructional feature of a synchronous machine. And then later you will be able to see the difference of a conventional machine with permanent magnet machines. After that, we will also look at the importance of rotating magnetic field, how it is induced and why it is important, which is the fundamental for 3-phase AC machine, but that is also equally important in a permanent magnet synchronous machine to understand the basic of this rotating magnetic field. Then we will look at the working principle of synchronous machine, both as a motor and generator. That should lead us to the equivalence circuit of a synchronous machine. And at the end, we will look at the steady state power and torque equation. And also it will briefly introduce you to how these equations or how what will happen when we look at the dynamics of machines, that when it is no longer steady state, but before steady state, a transient state, how do we handle it? So let's start with tearing apart a 3-phase synchronous machine. Most of you know it should have 2 parts, a stationary part, which is we refer as stator, and a rotating part. So stator at the simplest form could have simply total 6 slots, as you can see in the picture here. Maybe let me just turn on the laser pointer. Okay, so hopefully you can see the pointer. So you can see that in the simplest form of a stator, we could have just 6 slots and 2 slots for one holding a coil, one side of the coil that is current coming out of the phase, and the other one current going to the phase. So this is A phase, and then we have B and C phase. You can see that the location is at 120 degrees. You know, in 3-phase AC, there is a phase difference between A, B, and C phase, which is 120 degrees. But also their location in the stator, they are spaced at 120 degrees. That's very important. And the rotor for synchronous machine, there are 2 types of rotor. One is called uniform air gap rotor, and the other one is called salient pole rotor. So you are seeing the picture, that's the uniform air gap rotor, and here is the salient pole rotor. So uniform air gap and salient pole, in both cases, you can see their coils. Okay. In this picture, you can see the copper bar actually, which will carry the field current to induce the electromagnet in the rotor. In the salient pole, obviously you can see the poles, you can see the copper windings around it. When a current, DC current is passed through it, they will become your electromagnets, the rotor electromagnets. To see it is schematic, to understand why we call it uniform air gap or why salient pole, maybe these 2 pictures, it's good depiction of it. So you can see that in the cylindrical rotor, the air gap is near uniform air gap. So this is the cylindrical rotor and its representation. The cylindrical rotor, sometimes known as referred as uniform air gap rotor. In the salient pole, you can see the air gap just under the pole face is much smaller compared to the air gap in the interpolar region. And the poles are distinct or salient in the structure. So that's why the name salient pole. And they have quite different characteristics. So we'll start with our first, the basic understanding with a cylindrical rotor or uniform air gap rotor synchronous machine, which then will extend to the salient pole. Now, first, let's consider only the stator. We have 3-phase winding, but just first of all, consider, let's say we have just 1 phase, okay, A phase. And in all practical machines, actually, you could have your phase windings in more than 1 slots. In this example stator, you can see we have total 8 slots, 4 in the top and 4 in the bottom, and each slot carrying the conductor or the coils of phase A. Okay, so again, the top one showing current coming out of the phase, bottom one current going into the phase. And so this, when the current flows in these coils or windings, it's going to produce the magnetomotive force or MMF. Okay, and that MMF waveform actually looks like a staircase, as you can see here. So how does this why this becomes staircase could be understood easily. We'll do that in a minute. But before that, this type of winding in which the coils are distributed in slots are known as distributed winding. Okay, and this staircase MMF, if we look a bit closely, or if we do a Fourier analysis of this staircase waveform, we will see that the fundamental is going to be like a sine or cosine waveform. So that's why this type of windings are referred as sine distributed winding. And so now, coming to the point of why it looks like a staircase, you can understand that from the very basic Ampere's law. If we want to apply Ampere's law, obviously we will need a closed loop. Let's say that this is our closed loop of Ampere's closed loop to apply Ampere's law. And this is, let's say, when theta is equal to 0. So theta is an angle around the periphery of your actually air gap. Okay, so that's the air gap. All right. So we are starting. This is your theta 0 position. So that's at that position. This is the loop. And in the waveform, if we expand it, so we can see that's our theta 0 position. And at that point, you can see that the MMF, or the number of turns enclosed in your Ampere's loop, is total, in this case, the 8 number of conductors, or 4 slots, right? So that means we are getting the maximum MMF. That's the maximum point we are getting. Now, if we move one slot pitch and redraw this Ampere's loop, you will see that we again have same 4 slots, but now one of them is at the one of those slots is now actually with the current in the opposite direction. So total MMF enclosed in this Ampere's loop, this blue color Ampere's loop, is going to be less than what was when it is in the red loop. So that's the reduction which you will see here. And if we move to the 180-degree position, to the green loop now, that's this position. Again, the loop is actually enclosing total 4 slots of page A, but now 2 of them are carrying current in one direction and other 2 is carrying current in the opposite direction. So total MMF is again going to be 0. So that's how this waveform is happening, the MMF waveform. And this will repeat as we move along the theta. This will repeat here. So this staircase MMF, the fundamental of which is like a cosine waveform. Therefore, for a distributed winding, number of turns in the winding can be represented as a cosine function of theta, where theta is a angular position at the periphery of the air gap. Okay, so that it should have been number of turns in your slot times the cosine function of theta. If we would have an ideal cosine waveform like the one you are seeing here. However, our waveform is not actually cosine waveform. It's a staircase one. Only its fundamental is cosine. So we have to account for its staircase characteristic. which is actually the winding factor. Some of you may know what winding factor is. We'll discuss again later what it consists of, but for time being, you simply should know that number of turns in a three-phase distributed winding can be represented as a cosine function of theta, where theta is the angular position along the air gap. So when we have a number of turns like this, and if we allow AC current to flow in these windings, or current is a function of omega t, cosine function of omega t, or sine function of omega t, where omega is your radial frequency. That is, if it is 50 hertz, 2 pi times 50 omega. So current is cos omega, maximum peak value times cos omega t, this phase A current. And number of turns is n cos theta times the winding factor. So this is our MMF. Okay. So, and it's as per Ampere's law, should induce a flux density. So with a little bit of mathematical manipulation, we'll be able to show that this flux density, which is induced by this current at the air gap, is function of theta and omega t. And this is for phase A. But we will also have phase B and phase C coils or windings in the other slots. And they, when carry B phase current and C phase current, also going to produce similar flux densities. But in both those cases, omega, instead of cos omega t, will have a, in case of B phase, we will have cos omega t minus 120 degree. And instead of cos theta, we will have cos theta minus 120 degree. And for C phase, it will be plus 120 degree with omega t and plus 120 degree with theta. So the total flux density, that means induced due to this three-phase current, should be sum of A, B, and C phases. And when we do this summation by quite simple trigonometric relation, it can be shown that it will become the function of omega t, cosine function of omega t and theta, or rather omega t minus theta. So what this omega t minus theta represent is that your flux density or flux going to rotate around the air gap. So we can visualize it as if north, south, north poles are forming continuously and changing, which is, if we consider our flux density or our MMF as a factor, which is shown here as a red arrow, you will see that it's rotating in the space. So that's the rotating magnetic field. And we get this rotating magnetic field whenever there is a three-phase distributed winding carries balanced three-phase AC current. Okay, doesn't matter whether it is an induction machine, doesn't matter whether it is a synchronous machine or permanent magnetic synchronous machine. As long as we have a stator with three-phase winding carrying balanced three-phase current, we will get this rotating magnetic field in that air gap. And that's the fundamental of AC machines, because of which it rotates. It is so popular. It has dominated the industrial applications. You can also see a visualization of how the flux lines are rotating. In this type of animations, you can get easily from finite element analysis. So this is actually an animation of an induction machine and showing how the flux is starting. But similar animation we can get also for a permanent magnet machine or conventional synchronous machine as well. So that's the concept of rotating magnetic field. And it comes from stator. So we have to remember our stator is stationary. It has stationary windings, but when it carries three-phase AC current, it gives us a rotating magnetic field. We haven't considered our rotor yet, so we just have a rotating magnetic field. Now let's consider we put a rotor there, and we'll think how what happens. Oh, before that, this rotating magnetic field actually we can also visualize as a waveform, right? As we have seen in the previous equation, the flux density ideally should be a sinusoidal air gap flux density. The red, green, and blue are the bar phase flux density. That was BA, BB, and BC. And you can notice that they are actually pulsating. They are not moving. Our x-axis is theta. You can see, let's look at maybe the A phase, red phase. You can see that it goes to peak, goes to zero, and then to negative. But the peak is always at the same position. The black one is actually the resultant. When we sum up these three, we get that black one. And then you can see the peak of the black. It's moving, okay, in your theta axis. So that means it is rotating, okay? And so since it is like a rotating sinusoidal waveform, so we should be able to represent it also as a phasor. So, but this phasor is a rotating phasor, and it rotates in the space. So from which the concept of space factor was developed. And space factor concept is very one of the very important concept which is used to design controllers, to control inverters. It's even used in the even in power system control. Okay, so the space factor basically comes from this rotating magnetic field concept or rotating MMF concept. Some people try to describe it with just using the MMF, but I prefer to use it describing with help of the flux density. So that black phasor is rotating, which is the space factor, and which actually the representation of the rotating magnetic field. Now, what speed this is rotating? It is the synchronous speed. If any one of you do not remember what synchronous speed, here is the place to recall it. It depends on the frequency of the AC current. So if you have 50 hertz, then it will be 2 pi times 50. So that's the radial frequency. But if your pole number in the machine is more than 2, then you have more than 1 pole pairs. So in that case, electrical radial speed, which is 2 pi times 50, and mechanical speed, which is the real physical speed if you want to measure it, is not equal. It is mechanical speed is always smaller by factor of the pole pair. So if you have 4 poles, then if this is 100 pi, then your mechanical synchronous speed will be 50 pi because you have 2 pole pairs here, and it halves. If you have more than If you have like 8 pole pairs, it will be 1/8, and so. Okay, so as the pole pairs more than one, mechanical speed and electrical speed no longer same. But this is also another quite important things which you need, or which we will need when we will be looking at the control. So now coming to the rotor. So we have the rotating magnetic field, and then let's place the rotor in our air gap. The rotor, we could have a cylindrical rotor or we could have the salient pole rotor. Doesn't matter. In both cases, you can see that once we put the rotor, if it is a generator, the rotor will be rotated by your turbine. If it's a wind generator, wind turbine will rotate it. If it is a conventional system, then it could be a gas turbine. It could even be a steam turbine if it's a coal-fired power plant. So the turbine will rotate the rotor, and when it is rotating, there will be rate of change of flux. By Faraday's law, voltage will be induced in the stator windings. And when we connect this stator winding to our load, a current will flow to the load, which will be, if it's a three-phase, since we have three-phase winding, if our load is balanced, there will be balanced three-phase current, and that will create the rotating magnetic field. So flux that comes from the rotor, we can define this as a phi f, that is flux related to the rotor field. And the flux that is created by the current, that's a rotating magnetic field, can be represented as phi a. And the resultant of phi a and phi f is actually a resultant magnetic field in the machine phi. And since the flux and back EMF are related by Faraday's law, so there is always a 90-degree phase difference between back EMF and the flux from which it is induced. So the flux and the EMF for generator, this is our induced voltage or induced EMF. But for motor, also we will have the same induced EMF. And in motor, we call it back EMF. Okay. And also for motor, we need to make the rotor rotate. We do not have a turbine now. We need to create or induce a torque which can do mechanical work, turning a fan, turning your electric car, etc. Right? So where does this torque or force comes from? We can think now backward. That is, in case of motor, you supply the three-phase AC current to the stator. So first comes the rotating magnetic field. And then you have the rotor, which is own flux phi. So two magnetic fields interacts with each other. The rotating north and south pole of the stator tries to pull the north and south pole of the rotor, which is actually the torque. Okay, and that which we can use to do mechanical work. So interaction between rotor flux and stator flux gives us the torque or the force. So in both cases, we will, whether generator or motor, we will have back EMF or EMF, induced EMF, and the relation is, this relation is always true. The flux relation, EMF relation, and the current relation, which you can see here as a Pager diagram. The voltage that we see at the terminal of the motor can be thought of as a coming from this resultant flux phi. So this is voltage is 90 degree to this flux phi. And from that concept, we can actually go to our steady state equivalent circuit. So we have total flux phi, and this flux, since it is rotating or changing, so we will have rate of change of flux that gives us the voltage. But this flux is consist of stator current flux and rotor flux. So we have, and we know what is this rotor flux represents. It is the back EMF, EA. But what is this part, this rate of change of stator flux? What is this? If we do a little bit of, again, clear or a little bit of more manipulation, can quite easily show that this rate of change of stator flux is actually can be represented like a rate of change of flux with respect to a current, di dt, and this is actually change of flux linkage with current, okay? Because number of turns time flux can be a flux linkage, so rate of change of flux linkage over current. And that means this is a inductance. This is the definition of inductance. Inductance is flux linkage over current, right? So change of flux linkage, stator flux linkage over current. And so this inductance is in synchronous machine referred as the synchronous inductance, so LS. That means our voltage equation consists of the back EMF and a inductive voltage drop. And this inductance is not self-inductance, not mutual inductance, but synchronous inductance. We can represent this equation in steady state in terms of phasors. So then we will have a synchronous reactance, inductance time, the frequency omega, back EMF as a vector or phasor, EA, and the terminal voltage VA is also. So this equation we can represent by the equivalent circuit. Yes, and this equivalent circuit is known as the steady state equivalent circuit. All the quantities, that's voltage and current quantities, are vectors here, okay, and they will have phase angles and magnitudes. One thing we should know that this steady equivalent circuit can only be used for steady state analysis. We cannot use this equivalent circuit to design controllers, because controller will need to handle not just steady state, but also transient, that's the acceleration. So we should remember here that steady state equivalent circuit is good to analyze steady state performance, but not useful to design actually dynamic performance design controllers, that is to for the particular dynamic performance, okay? And also we should quickly recall what is the synchronous inductance. So I said synchronous inductance is not self-inductance, not mutual inductance. So what it is actually. So for that, we have to look at what is this flux linkage with the A phase that we have shown in the previous slide. Number of turns of the A phase and the flux created by current IA. So this flux linkage is actually includes the self-inductance of the A phase, LAA, and the two mutual inductance with A phase, that is LAB and LAC. In a three-phase machine, there is a straightforward relation between the self-inductance and mutual inductance. And mutual inductances are usually minus half of the self-inductance. And since we are using a balanced three-phase current, so this relation, sum of the three currents are always zero. So using the relation of the current and using the relation between self-inductance and mutual inductance, we can easily show that this equation 2.10 can be written as 3/2 times self-inductance times the phase A current. So this 3/2 times self-inductance is actually the synchronous inductance. So synchronous inductance includes both self and mutual inductance of a three-phase machine. And that's what we see in our equivalence circuit. We can also draw phasor diagrams from the equivalence circuit. As I said, all our voltage and currents are phasors here. So conventionally, the terminal voltage VA is taken as your reference phasor. Your current, the stator current, could be leading or lagging the voltage depending on our, in synchronous machine, it actually depends on whether it is a overexcited or underexcited synchronous machine. Here you are seeing a lagging power factor condition. That means current IA is lagging voltage VA. And so that theta I, or the power factor, is our power factor angle. Then the phasor phase difference between the voltage V, terminal voltage VA, and back EMF or EMF EA is delta. And this delta angle has a big implication in synchronous machine. This delta angle we can also thought of as it is the phase angle between our rotor flux, because rotor flux gives us EA, and the resultant flux, which gives us VA. So delta angle is the phase angle also between rotor and the resultant flux, rotor flux and the resultant flux. We will see, or it could be shown from using the same equivalence circuit, that the torque and power are function of this delta angle. We'll see that in a minute. But before moving to the power and torque, let's see what happens if we have a salient pole machine. In the uniform air gap machine, that we have one single synchronous inductance or synchronous reactance. But when we have a salient pole machine, since the air gap just below the pole surface is much smaller compared to the air gap at the interpole space, the reluctance, magnetic reluctance, obviously is much smaller here compared to the interpolar region. So if we have less magnetic reluctance, that means we should see much larger inductance. So that means at this position, the inductance, the synchronous inductance is much larger compared to the inductance at the interpole region. So that means we have two synchronous inductance here, or synchronous reactance. And so to define those two, we take help of the direct axis and quadrature axis concept. So for salient pole machine, we define the interpolar region as our q-axis or quadrature axis, and direct axis is defined along where you have the minimum air gap. So when we have two synchronous reactances, d-axis reactance xt and q-axis reactance xq, obviously we have to also define or draw our phasor diagram considering those. And the easiest way to do is decomposing the current, the stator current, the phase current into two components, ID and IQ. So direct axis current ID, quadrature axis current IQ. So resultant is our phase current I or IA. All other things, that is the flux in the due to the rotor, EMF caused by the rotor flux E, that relation still remains same. But now we have the reactance drop due to ID current and XT reactance and IQ current and XQ reactance. So together, with the back EMF, and here we are just ignoring the rotor resistance, because usually rotor resistance could be much smaller, especially in large synchronous machines. So that resistive drop, I times R, can be neglected. So this, when with that negligible rotor, negligible resistive drop, when we combine back EMF and the two reactance drop, we get our terminal voltage phasor. And again, you can see that same delta angle present. That is the phase angle between EMF and the terminal voltage P. And one important thing to notice here, since we are now decomposing the current into ID and IQ, we can also define a current angle. This current angle is angle between current phasor I and EMF or Q axis. And this is usually used as a gamma angle. And in PM machine, this gamma angle has much more importance than the load or torque angle delta. In the controllers, we actually try to get an optimum value of this gamma angle. So that's why this understanding this phasor diagram for salient pole synchronous machine can help you to understand the PMS machine's model, as well as its various control algorithms, when we'll discuss in the next day or day after. Okay, so that's why it's important to understand this phasor diagram of a salient pole synchronous machine. Now, we can quite easily find the power and torque of a synchronous machine using the steady state equivalent circuit and its phase relations by finding in synchronous machines are used more as a generators. So conventionally, this power can be calculated from finding the complex power and using from the same equivalent circuit. And the real part of the complex power is the developed power in a, if it's a motor. If we divide this developed power by speed, in synchronous machine, speed is always your synchronous speed only. So dividing this power by synchronous speed, we get the torque. So quite easily, power and torque expressions can be found from the equivalent circuit. And this power, this real power, is also our familiar power expression, that is voltage time current time power factor. That expression is still correct, but we can write power for synchronous machine in terms of also the back EMF, synchronous reactance, and the delta angle, the angle between E and P. So this expression, from this expression, we can actually see how power and torque both are function of that torque angle or load angle delta. And we can see that they are sine function, okay? Which means if we want to get maximum torque from a synchronous motor, we will keep this delta angle to the 90 degree. So 90 degrees, sine 90 degree will give us the maximum torque. And in case of generator, if we want maximum power out of our generator, we will again keep this delta angle 90 degree. Same power and torque expression for salient pole machine. If we develop, you will see that it has an extra component. Okay, we compare these two, you'll see that it has an extra component. So this is the there should be a 3. This 3 was missing. Sorry, this is the typo. Okay. So it's still, this is 3-phase developed power for salient pole machine, and that part and this part is exactly same, but then we have an additional component. Similarly, in case of torque, they are same, but just only difference here is that the synchronous speed in this expression was done with the electrical speed omega divided by pole pairs P. So the synchronous speed can be written as omega over pole pair. So that's why it looks a little bit different, but actually it is exactly the same expression as this, what we are having here. But then we again have an extra component. So this extra component is actually coming from in salient pole machine due to the difference in reluctance in the D and Q axis. So that's why the second component is called reluctance torque. Okay, and first component is sometimes referred as cylindrical torque. In case of permanent magnet machine, this part is called actually magnet torque. It comes from the magnet. And magnet will give us this EMF E, because instead of field current, which gives us the field flux by air, in PM machine, this will come from the magnet. So if we plot the torque and power against the load angle or torque angle delta, for a uniform air gap machine, you can see that maximum torque or power is going to happen at delta equal to 90 degrees. But for a salient pole machine, that's not true anymore. For a salient pole machine, the maximum torque or maximum power can happen at an angle lower than 90 degrees. Okay. And also this torque versus delta angle, we can see one more thing. In conventional synchronous machine, we can increase the magnitude of EMF EA by increasing the field current, because it's coming from our field current or rotor current. So as the EA increases, the peak of the torque can be increased. And if we have zero field current, that means we don't have EA at all, zero EA, that means the first component of the torque doesn't exist. We only have the reluctance torque. So the reluctance torque waveform will look like what you are seeing here. And you can see that in the reluctance, if we only have reluctance torque, then the maximum torque will happen when delta is about 45 degrees. Okay, because we only have this part. So in reluctance machines, we only have this component. We do not have this part. And the torque speed characteristic will be similar to the one you are seeing here. Whereas in a PM machine, if it is a salient pole type characteristic, if it has salient pole type characteristic, then it would have a characteristic like this, with back EMF or with EMF EA equal to 1. And we cannot change the magnitude of EA by increasing current there, because we have fixed magnetic flux, and which comes from the permanent magnet. So that brings us to the review of the first part. So let's think what we have discussed, and then we're going to take 5 minutes break before going to the second point. And if you have questions, you can ask, or you can use the chat as well at this point.
So thank you, madam. So we will take for 5 minutes break, madam. Is it not?
Yes, we'll
Yeah,
take a 5 minutes break. So that is now I think at India it is 11:33.
Yes, madam.
So we will be back at 11, let's say 38.
11:40. Okay,
11:40. 11:40. Yes, 11:40 is fine.
Okay. Okay.
Yeah.
Okay.
But I would like everyone to take those extra 2 minutes to reflect on what we have just discussed, and then take 5 minutes break.
Okay, ma'am. Thank you, ma'am.
Think about also if you have any questions on what we have just discussed.
Okay, ma'am. So the participants, 5 minutes break for you. If you have any questions, you note down the questions. After this break session, madam will answer the questions.
Yes. Okay. Thank you.
Thank you.
Thank you, madam, for this session.
Right. Thank you.
Madam, are you there?
Yes, yes, I'm back here. Yeah,
Yes, madam. Shall we start, madam?
is everyone back?
Yeah, almost.
Okay. Any questions? I have gone a little bit faster, I know. We have a lot to cover, not enough time, I
But-
guess. So I'm going fast.
Participants,
So if you have
anybody
any
having any
questions.
questions regarding this session? So if you have any question, you write down in the chat box. So later, madam will be addressed. Madam, you start, madam.
Sure. Yes, if you have question, you can also use chat and put it there.
Yes, madam. Later.
Yep, sure. Thanks, Raju. I am not sure about the background of all of you. So I hope that many of you have at least have studied synchronous machine in your undergraduate or even in the master's programs. Because if you haven't, then please do. And if you're finding it difficult, what I have just discussed, so please you can refer to textbook, or of course you can also always ask me questions. And do not worry if it is a basic question; it's fine. It's always better to clarify basic question, and you should know that there's no silly question or basic questions. That all questions are good. Okay, Himanshu, yes, do you have a question? I can see a hand raised.
Yeah, Himanshu, please ask question. If you have any question, Himanshu. I think, madam, he raised. That means he knows that they have studied their synchronous missions in their undergraduates. Maybe in that
Okay.
aspect they have raised the hand.
Okay, that is good. If anyone else also want to do that, so I know.
Yes, yes, madam. Okay, madam, you carry on.
Now let's move to the second part. Himanshu, you are not audible before. He has put a chat. Do you still have a question?
Himanshu, you have any question? I think.
Oh, he has a question. So yes, you can put it in the chat window if we can't hear you at this stage.
Yes, your voice is not audible. You please write down the question in the chat box. Then madam will answer.
I will go back there later, but without wasting time, maybe we'll just proceed for time being, and I'll have a look at Himanshu's question later. So next half, we're going to look at the permanent magnet material, and then we will look into the permanent magnet machines, actually how it is different from synchronous machine, its working principle, and also we'll be looking briefly how the permanent magnet synchronous machine and brushless DC machines are different. Now you can see a picture here of permanent magnet materials. They have different size and shape. Initially, when the permanent magnet like materials were developed, the one of the constraint was that we have only certain shape and we have to build motors just using those shape. But that constraint has been removed now. The manufacturing of magnet has now developed to a quite different techniques they are using. So because of that, they can produce any shape, which means it's quite easy to get any shape. So in fact, they can now melt down the material and then can put it in mold. So that's why we can get any shape, whatever we want. And the development of magnet material is quite interesting. If you can look at here in our left-hand side picture. Electrical steel or steel material is known to us, the industrial world, since early 1900th century, 1910, 1920, the steel materials were developed. But if we look at the magnet material, the high energy density magnets such as neobidium, iron boron, or Semco material, they have come only in late 1990 or 2000 about. Okay, so nearly 100 years difference here. So apart from this high strength material, there are other known magnet materials. One which is very commonly found, which you can even find in the freeze magnets that you can buy with just a few rupees. That's the ferrite magnet. Okay, their energy is much less, but they're cheap, and they can also be quite easily demagnetized. And other end, we have the Alnico and Semco and NdFe boron, neobidium boron. These, out of them, neobidium iron boron is the highest energy magnet. You need a very large current, negative current, to demagnetize them. So they are very difficult to demagnetize, in one word. But they give you a much larger flux density. So that's this graph here shows the various materials where they sit in terms of H, the negative magnetic field that you have to apply, or positive magnetic field that you have to apply to magnetize rather in this picture, and the remanent magnetic field that you can find in a magnet when the magnet is in free space, not surrounded by iron or steel. So what's the magnetic field inside it? That's the remanent magnetic field. You can see that the highest you can find from the neobidium iron boron, and it also takes the highest current or magnetic strength that will be required to magnetize it is highest, as well as the exact same, if we apply in the negative direction, will be it will be demagnetized. And the lowest is the ferrite. It has only about 0.5 of a Tesla compared to nearly 1.25 Tesla for neobidium. And they also can be demagnetized very easily. They need only less than 500 kiloampere per meter to demagnetize, compared to nearly 2000 kiloampere per meter for neobidium iron boron. So obviously, we can see that the choice for high performance permanent magnet motors is neobidium iron boron. This concept of remanence and the corrosivity can be also understood with help of the hysteresis loop or BH characteristic of the magnet. So you can see this is actually a BH characteristic of a permanent magnet, and it's much wide. Okay, if we compare this to a pH characteristic of a steel material, this H part is much larger, which means that they need a very large field to magnetize and demagnetize. And the remanence, that what we talked about previously, is the flux density. When you remove the H field completely, whatever is a remaining B in the magnet. So when H is 0, what is the remaining B in your magnet is the remanence flux density. And the negative magnetic field that you have to apply to bring that remanence to 0 is the corrosivity. Okay. For a magnetic material, like probably you know about the pH characteristic and the pH graph. For a magnet, permanent magnet, when we say pH characteristic or pH curve, we only actually refer to this portion, okay? And this portion, if you look a little closely, it looks like a linear graph, a linear curve, okay? So, and most of the time, magnet operates in this region only. So that's why this is what is interesting or important characteristic for a permanent magnet. We do not need to look at the whole pH loop, since it doesn't magnetize or demagnetize easily. So it's no point looking at the whole loop. And this part is known as also demagnetizing curve or characteristic of the magnets. We have discussed a little bit, I think, in the last electromagnetic refresher lecture about the load line and a graphical method. So a load line can be drawn also for a magnet, permanent magnet material. And from that load line method, we can find that it is a function of the length of the magnet. So that's your length, and the cross section of the magnet. And if we consider a very simple magnetic circuit like the one you are seeing here, we have magnet in one side and a small air gap in the other side. Using this, we can find what is the operating point of the magnet in this circuit. And how do we do that? By using the load line method. So that, for example, let's say this is our, we have drawn the load line and we found that this is our operating point. So by changing either the magnet length or air gap length, we can obviously change the slope of this load line. It can move either that way or this way. So if the operating point moves towards the bottom side, that means it is coming closer and closer to becoming demagnetized. So you want your operating point somewhere here rather than to be closer to demagnetization. And when you design permanent magnet machines, so this can help to tell us where your operating point is. If we compare the different type of magnet material, we have seen in the previous graph as well, that highest is materials such as Neobitium and Semco, and in the lowest is Ferrite, but we haven't talked about Alnico. So Alnico is an interesting type of magnetic material. it can be quite easy. It has high flux density, but very low corrosivity. So that means it can be easily magnetized and demagnetized. And in recent times, there are proposals for permanent magnet machine using alnico. And those machines are known as flux changing or flux switching PM machines. So you can magnetize or demagnetize the magnet in the machine using current, which is kind of like having a control over your rotor flux, like we have in conventional machine. But this is still quite a new area. It has not been commercialized. There are some research going on, especially in the US under Wisconsin Madison University. They have done some work on this type of machine, but I think still quite a way to go for flux switching machines. Another important things to we mentioned last time is that the temperature, the magnets, especially the high density magnets such as neobidium, iron, boron, they are very temperature dependent. And as the temperature increases, you can see that their magnetization, demagnetization characteristic changes. So this, the one that we have seen in the previous slide, that linear characteristic, this is at 20 degrees. But as the temperature increases, you can see that the demagnetization, the part that is the bottom part, becomes much nonlinear, which indicates that means if you are operating your magnet at 50 degrees, it has the chance of demagnetization has increased, because previously if you need let's say certain negative Hc when it was operating with 20 degrees, now if you apply the same Hc but your magnet is at 50 degrees, it will already be demagnetized, whereas previously it was operating closer to demagnetization, but not yet demagnetized. Okay, but as the temperature increased, that negative H becomes smaller and smaller, and the temperature at which permanent magnet can become completely demagnetized, known as Curie temperature. So you do not want to operate your magnet closer to Curie temperature. So a NdFe boron or neobidium boron material, the Curie temperature is close to 120 degrees. That's why you do not want to operate you do not want your magnets to be closer to 100 degrees. In fact, that is always, you want to keep a safe buffer. So allowed temperature in practice is about 80 degrees, no more than 80 degrees for any permanent magnet machine, especially the rotor temperature. So you want to monitor the rotor temperature if the motor is designed with very aggressive characteristic. Okay. We can also compare the demagnetization characteristic of the neobidium, Semco, and ferrite. And again, you can see the ferrite, it's much smaller and it demagnetizes quite easily compared to neobidium, iron, boron. So choice is neobidium, iron, boron. Semco could be used, but it is actually more expensive than neobidium, and it gives less smaller remanents, and it also has smaller negative Hc for demagnetization. So it doesn't give you value for the money. So that's why it's not a popular choice. Rather, most of the PM machine is uses neobidium iron boron. There are different types of neobidium iron boron actually based on how they are manufactured. So most common one is bonded neobidium and sintered neobidium. So sintered neobidium is actually more robust mechanically compared to bonded one. And also the remanent flux of a sintered neobidium is higher than the bonded one. But bonded one could be sometimes useful for certain applications. The main composite of a neobidium iron boron, probably you can already understand from its name. It has iron, it has boron, and it has a rare earth material, neodymium. However, the neobidium is not the most expensive or most difficult material, but actually another material which is required to make a neobidium iron boron material, and that is dysprosium. And the dysprosium is means it's even rarer than neobidium iron. And last time, nearly 10 years back, there was a crisis, and because the dysprosium was that the supply to dysprosium was there was an issue with it. Again, it was actually from China, and that has pushed the price of rare earth material to a much higher value compared to previous years. But that crisis was brought down, and then again price stabilized. But this can happen again in future. So that's the reason why in the recent years the dependency to the rare earth material you want to reduce if you can design motors with much smaller amount of magnet or no magnet at all will be and can give the same performance will be very good. Of course, we are yet to invent such a motor. There are proposals to use even ferrite as in opposition to the neobidium iron boron, because ferrite is cheap, ferrite is available everywhere, it gives you the same efficiency, but if we use ferrite, as you can see from the previous slide, that ferrite has much less energy. B times H is much smaller compared to neobidium iron. So your machine size going to increase if you use ferrite. And of course, it will also can get demagnetized easily. So that those are the two main issues with ferrite. If we want to replace it, replace neobidium iron boron with ferrite. But the advantage is that it's cheap and it is not temperature dependent as neobidium iron boron. So that's a brief introduction to the magnet materials. Now we are ready to look at actually the permanent magnet machines. In the meantime, maybe I'll quickly look at what was the question. Okay, so Himangsu has a question. Is this the similar question as what you have yesterday, Himanshu? That you think the reluctance machine could be superior to the PM machine? I think I explained it yesterday. It is to a certain extent, yes, but then you only have reluctance torque. So if you want to get the same torque as the permanent magnet machine, you need to push much more higher current in those machines. So when you push higher current, that means its copper loss, I square R loss increases. And also the machine needs to be much larger because it has to hold those conductors that can carry that large amount of current. So the machines need to be bigger, and machines also, the copper loss is significantly high. And the other problem is the torque is not as smooth, so gives us noise problem. So that's the problem with reluctance machine. But it is a good option, alternative, if there is problem with rare earth material. We'll discuss a little bit about reluctance machine when we talk about magnet machines, permanent magnet machines here. So if we look at the history, the PM material first appeared or invented quite sometimes back in 1960s, 68 to be specific. But it was not used in the electric machines for some time. In 1983, first a spoke type permanent magnet machine was proposed by K.J. Bean. But that time, most of the industry and nearly all academia rejected it, kind of. They were saying that it's not going to work. Then in about similar time, the permanent magnet material were used in the conventional brass DC machines. If you may recall that in a conventional brass DC machine, the field or electromagnets are in the stator. So those electromagnets can be easily replaced with magnet material. And we have then permanent magnet DC brass commutator motors. They are still available. You can buy PMDC motors, PMDC brass motors. But then the problem with the carbon brass was quite well known, that in the DC motors, you have much higher maintenance because you need to replace those carbon brasses every 6 months. So that's really a very big maintenance cost, especially for industries which need to run for 24 hours, 7 days. You have to stop the motor, replace the carbon, and then run it. So which could require you to stop the whole process of your production. So that's why the scientists and the industry was looking for an alternative, how not to use the brasses, carbon brasses, and still have the same good performance as a DC machine. That brings us to that PM brushless motors. Okay, so PM brushless DC motor were developed, but at the same time, actually, the other type of motor, which is the PM synchronous motor, was also developed. In the PM brushless motor and PM AC synchronous motor, you will see that they are quite similar. There's only a slight difference in the stator and their control. Discuss them that in a minute. So after that PM brushless DC machine and PM brushless AC machine, there was nearly nothing till 2003. Okay, because the PM synchronous machine was found to be okay, efficient, can be replaced some conventional motors, but they were expensive. They needed inverter drives. They can't run online, without converter, just like a line start motor, like other conventional motors. So that's why there was no push for PM machine to develop further. But then around 2002-3, this there was the concept of EV was coming. There was the need to find a machine which is efficient, but also can provide that constant power speed range or the flux weakening. Even so, that actually lead to a lot of development. One of them was that development of a new type of stator known as fractional slot concentrated ion type. We'll discuss this a little bit later. And so that was first used with a surface type magnet machine. We did quite a lot of work also with the fractional slot winding, concentrated winding machine, but for IPM machine, and that was around 2011. So we were actually, our research group was one of the first to experimentally verify concentrated winding IPM machine in our labs. And now that the distributed owned PM machine is commercially available. Concentrated owned PM machines are also coming in the market, but there's still quite a lot to understand about concentrated winding machines. It's not, we can't say that it is a mature technology yet. We discussed yesterday the difference between the two type of PM machine. The one is when the magnets are glued on the surface of the rotor, known as surface type. And if the magnets are buried in, we get the interior type. So in the surface type, it behaves like a uniform air gap synchronous machine. Okay, the reactance, D-axis reactance and Q-axis synchronous reactance are equal. Although it looks like from the first look, it should be a salient pole machine, but it's not. So we'll discuss this, why it is not in a minute. Whereas the interior type PM machine actually behaves like the salient pole machine. And we'll see how those two are comes by. Then the reluctance machine, which we have talked a little previously. So if we do not have magnets, we can shape the rotor like a salient pole, but you can see it has no magnet or no winding. Then it is a reluctance machine. If we have a three-phase stator, we get a synchronous reluctance machine. If we have a special type of stator, then we get a switch reluctance machine. Okay, so we can also have a reluctance machine with somewhat similar to a interior type PM machine, but without the magnets. Okay, instead of magnets, we just have some air here, or just hollow these parts. And this is another actually reluctance machine. Sometimes, as I mentioned, if you want to produce the same amount of torque as a PM machine, you need to push much, much higher current. So sometimes they put very thin, light, rare earth magnets in this place, that those slits that you can see here. So, and then they are called a PM assisted synchronous reluctance machine. So for me, PM assisted synchronous reluctance machine and IPM machine, there's not much difference actually in terms of its working principle, control, all the things. Only difference is that the in synchronous reluctance, the reluctance torque component is larger compared to the magnet torque part. Now, the brushless DC machine and PM synchronous machine surface type, if we tear them apart, the rotor you will find will be exactly same. It's a surface type rotor for both brushless and PM surface type synchronous machine. But there is a difference in the stator, especially those who are small brushless DC motors. The stator usually have these windings, as you can see, they are tooth wound or concentrated type, that the windings are wound on the tooth. Whereas in the synchronous machine, we have the windings distributed over a number of slots. Okay, so stator is different, results in the induced EMF or back EMF waveform for a brushless DC machine to be like a trapezoidal waveform, okay, compared to a synchronous PM synchronous machine in which back EMF is nearly sinusoidal. That's the first difference. Back EMF waveform is not sinusoidal in BLDC motors, especially BLDC trapezoidal back EMF motors. So sometimes they're referred as BLDC, sometimes they're referred as BLDC trapezoidal EMF motors. Whereas sometimes this PM synchronous machine with sinusoidal back EMF also referred as BLDC, provided they have very simple control. Okay, so that's why sometimes people confuse the PMSM and BLDC to be same motor. However, in reality, they are not. So difference is they could, in the BLDC, the control is simple, as I said. So the controller or the inverter actually gives square waveform, whereas in a PMSM, you will get a nice sinusoidal current. And the operation for BLDC motor is more like a DC motor. The only difference is that instead of brush commutation, now we are having electronics commutation through the inverter. Both motors behaves like BLDC and PM surface motor, both behaves like a uniform air gap motor, non-salient type, okay? And they do not have any CPSR or constant power speed range. So they are not good to be used in electric vehicle applications. And they could have very large ripple in the torque. So as I mentioned earlier, their movement is not smooth. They have a jerking in their rotation. So that could translate to a vibration. As the smooth torque, it may not be available, which is sometimes fine for some industrial applications, whereas maybe in a EV, you want a smooth driving. You do not want your car to move with a jerk. So that's another reason why you want to reduce the ripple in the torque of the EV motors, EV traction motors. Since we have a trapezoidal back EMF for brushless DC motor, so to get the maximum torque, usually the current is commuted in such a way that it gives you a square waveform. Okay, the output of the inverter is a square waveform or wave current. So since the waveform shape is pretty much known for BLDC motor, so we also know where to start the electronics commutation in the inverter. So 30-degree, 150-degree, and so on. So about 120-degree difference between the two commutation points. And because this is already known where to commute, so we can use Hall sensors to determine where exactly to turn on our inverter switch. And that makes it cheap. You don't need sophisticated position sensors such as encoder here. But the PMSM machine cannot operate like this. They need a continuous position detection. And that means you need an encoder. Or you have to estimate the position from current and voltage very accurately for a high performing PMSM machine. And since your current is not sinusoidal and back EMF is also not sinusoidal, so for BLDC machine, the torque you can see is not smooth. Okay, it has quite a lot of ripple. So if we want to go with BLDC machine, we have to live with it. We will have unsmooth torque. On the other hand, if it is a surface type synchronous PM synchronous machine, then your inverter need to operate in the normal way. That means it need to it can be switch on and off using either sine PWM or space vector modulation. We need particular control to operate these inverters using SPWM or SVM. And since these controls actually based on the Park transformation, which we'll talk about later, so that Park transformation needs the information of position very accurately, the rotor position, and that's why it requires encoder. It cannot operate with only Hall sensors. But now our waveform, current waveform, output current waveform of the inverter is sinusoidal. We also have our back EMF sinusoidal. So torque that's developed is much smoother. If you compare the previous torque and previous figure and this for the two motors, you can see it's nearly DC, constant DC torque. So you get a much smoother torque in a sine wave PMSM. So surface type PMSM is pretty good as long as we do not need CPSR, constant power speed range. And they are very good also for wind generator. In wind generation, we do not need CPSR. But then in EV, as we discussed yesterday, this requirement of constant power speed range, which we can get only using the other type of PM machine, that's the interior type. And the difference, as we have already discussed, the magnets are buried in the rotor. In terms of the rotor topology design, so I'll come back to this slide in a minute. The SPM, you can see that there's not much variation, okay? The slight variation in the SPM, only the magnet shape is slightly different compared to this two, let's say, or we could have a magnet, a cylindrical magnet all around, or we could use the magnet's orientation in a somewhat differently compared to this one. This is a normal surface type PM machine. You can see that magnetization direction of these magnet pieces are just going inward or outward. But if you compare here, the magnetization direction of each piece of magnet actually kind of coming out, going from left to right and then going in. So these three pieces together actually forms one pole. So this type of arrangement known as Hallbeck array. So the Hallbeck array gives actually very high air gap flux density at the air gap. And so Hallbeck array has been proposed to use to design permanent magnet machines, which can be made very light and also very compact. So that's mostly the variation in surface type PM machines, rotor topology you can see. Whereas if you look at IPM machine, there are many different topologies. The one which was first proposed is this flat type. And in fact, the first one is the spoke type. This is in 1980s that proposed by Bean is this spoke type. But later this flat type become very popular. A slight variation, the inset type has been also proposed. But in more recent types, this V shape has become the dominant type of IPM machine. We can have also multi-layer of magnets as shown here. So this multi-layer magnet IPM machines are very similar to actually synchronous reluctance rotor that you have seen. So there's very little difference in the topology. But this is not all. There are still new type of rotors are being invented. Under flat type, there are so many different types. Okay. Similarly, in V type, there are so many different V shapes coming up. Spoke type is not much variation, although there are some new designs based on that how to keep them in the rotor structure more robustly. Based on that, some new designs has come up, but the magnet topology is pretty much same for spoke type. And then the multi-layer, there are again so many different types are coming. So for IPM machine, there are many different rotor topologies. We haven't settled down on one single one yet. It is still evolving, the rotor topology for IPM machine. So that's like every now and then it comes a new topology. And this is pushed by actually EV traction motors. So like nearly all the major automotive companies are using IPM machine, and they all have developed their own rotor topologies and patented it. So that's also pushing this rotor, IPM rotor, to have so many different topologies, magnet topologies. Now let's go back to the theory part where you can understand why the surface type behaves like a cylindrical motor compared to a IPM machine. So if we look at the flux path here, this flux path can be generated by finite element analysis. Okay, so if we look here, you can see that the flux, magnet flux, when it is crossing to the stator, it crosses the magnet and the air gap and then goes to the stator. So the magnet's permeability is same as air. So for the magnet flux, or the magnet itself, behaves or it experiences like having an extra large air gap on its path, since permeability of magnet and air is same. So that's why this is for the magnet flux. This is like a large air gap, uniform uniform air gap synchronous machine. Whereas if you look at IPM machine, the flux has to cross the magnet, go to the iron, cross again the small air gap, and then go to the stator iron. So the flux sees the magnet and the air gap and iron. So this here, if we call this is our d-axis, the reluctance is much larger compared to the q-axis, the interpolar region. So for IPM machine, the d-axis reactance is actually smaller than the q-axis reactance. This is opposite of a salient pole synchronous machine, but it does see reluctance in its flux path, and that's why it behaves like a synchronous pole reluctance machine, and it has that reluctance torque. So because of which we can use it for doing or achieving the wider constant power speed range. We can do flux weakening, but those things we can understand only when we look at its dynamic model. And that we will do tomorrow's lecture or day after tomorrow, one of those 2 days. And one last thing is that before we finish for today, I mentioned this, I think, briefly. In the space of stator, there's no innovation happening. We were using distributed winding for a long time, but in about 2003, the concentrated windings were used in BLDC motor, if you have recall, but they were not used for 3-phase AC synchronous machine. But in 2003, it was proposed that by using concentrated winding in the stator for even for synchronous machine, a few things can be achieved. So we know that surface type permanent magnet machine doesn't have any CPSR. But if we use a concentrated winding in the stator, we can in fact achieve a condition which is required to get wide constant power speed in a synchronous machine. And this condition you will understand when we'll discuss the dynamic model. But for time being, you should just know that the ratio of the magnet's flux linkage over the d-axis inductance, synchronous inductance, gives us a current. This current is sometimes known as short circuit current of synchronous machine or characteristic current of synchronous machine. If this characteristic current can be made equal to the rated current of the machine, then we can get theoretically infinite constant power speed range. So when the concentrated winding was used, so what it did is that it actually increased this d-axis inductance by increasing the leakage inductance in the machine. And so when you increase this value, that means the characteristic current could be brought to a relatively smaller value, and could be made it equal to the rated value. So that's why the concentrated winding machines has become popular in recent times. But again, as I said, it's not yet commercialized fully. There's still quite a lot to understand, because with concentrated winding, the magnetomotive force, the MMF waveform, which you have seen in the beginning, the staircase waveform, that is no longer staircase waveform. It has many more harmonics if we do a Fourier analysis of MMF of a concentrated winding, and they have different effects. So those were not yet fully understood, but it has been proposed, and it was, as I said previously, we have actually done quite a lot of work on that concentrated type winding, and we saw that how CPSR can be extended. So our initial distributed on PM machine, which was that, and it has only very little constant power. Then in around 2006-07, we proposed a new type of rotor topology, but still using distributed winding. We are able to extend the constant power speed nearly to 3 times. But it was still not sufficient. We needed at least 5 times. So later, when we experimented with concentrated winding, we were able to show that even in IPM machine, we can increase the constant power speed range. And now we could make it 4 times bigger, and with better optimization, it can go to even 7 times or 5 times. What was proposed was 5 times, but we later were able to even push it to the 7 times. So there are some advantages of using concentrated winding. And I think this brings us to the end of this part of the lecture. But what we see that basically PMSM is a synchronous machine. To understand its working, we need to understand synchronous machine. The high energy density PM material actually has helped to push the development of PM machines. And the IPM machine compared to surface type has many different rotor topologies. And these are due to that quest for increasing the constant power speed range in traction application of EV drives. Okay, so that's I think the end of today's first part of the lecture. Do you have any question?
Any question from the participant?
So any questions from the participants?
No, sir.
So
No?
No, madam.
no questions.
Yeah, so it's probably a bit difficult one, and you need your head around a little bit to think about. So hopefully you will get some bit more practice in the tutorial, which those some of those theory in the afternoon.
I think okay, madam. So I think we will stop.
Sure. Okay, we'll stop and then we'll see you.
I think participants, if you have still any questions, you can chat with the madam in the tomorrow class also, because tomorrow also madam is going to deliver the next session. So meanwhile, if you go through this and if you have any questions, so we can ask. Okay. So
Yeah.
Madam, thank you very much, madam.
Thank you. Just one thing. We are not providing the materials to the students. So have we decided how to do that?
So
Okay,
recording
madam,
material, madam.
Madam,
Sorry?
material I can discuss with you. So as per our discussion, you will send the PDF copy.
Okay.
We'll make a book type things here, and that will be given to participants.
Okay.
Okay.
Okay. Okay.
So,
All right. So that's fine.
all of you, madam, another thing, Our next session will be from 1:45 or 1:30.
1:45 is fine, I guess, right? Because it is now
Okay.
12:40,
Okay.
right?
Okay.
So one
Yes, ma'am.
one
Okay.
12:40.
one hour. So yeah, 1:45 is
1:40.
fine.
Okay.
Yep.
Okay.
Fine.
So, so there is a problem. Say if we give say same Zoom link, so that's why I am giving separate Zoom link in the morning hours. Similarly, in the second half also, I shall send the separate Zoom link.
Okay.
Okay.
It should be
So,
fine.
okay.
Please do send it to Clay as well so that he
Okay.
becomes
Okay.
aware of
Okay.
it.
Okay.
Yep. So see you maybe in
Okay.
the 1 hour time, and then we'll
Okay.
start
ma'am.
up the tutorial. Thank you very much.
Thank you.
Thank you, madam.
madam.
Thank you very much for your valuable lecture. So
Thank you.
participants, you take 1 hour break. So then you join after 1 hour. Thank you. Thank you, sir. Thank you, sir.
Thanks.
Okay. Thank you.
Okay, sir.
Madam, is it that recording option is with you? Since I make you host for this, so you see the recording option. Is it okay, or it is
Recording. I'm just checking.
recorded? Okay.
It's recording. Yeah, it's recording.
Yes. Okay. Okay.
Maybe
Okay.
you can also change the host back to Dr. Silchar, because otherwise I have to end the meeting for all. I cannot leave the meeting without ending it. So if you
Okay.
revert it back to yourself,